So welcome back, Level 2 NCEA Physicists, continuing on with Level 2 Mechanics and looking at forces and shapes. So in terms of forces and changing shapes of objects, if you apply a stretching force on Mr. Stretchy Man, for example, here, then you will say that Mr. Stretchy Man is under tension. Whereas this tennis ball here is being squashed, the object would be under compression. Okay, so there's 6 major properties that materials have. They can be brittle, like glass, which means they don't change shape easily, they just break. They can be tough, like the rubber ducky. You can kind of manipulate with forces the shape of a rubber ducky and it'll be fine, won't break easily. Elastic materials, like the elastic rubber band we see in this kind of sporting equipment, will return back to its original shape once that tension force has been removed. Plastic materials, like plastic bottles, they retain the shape that they've been molded in quite well. And then, at least for metals, ductile materials can be drawn into wires, like the copper wire here, and malleable materials, like the gold foil here, can be hammered into very, very thin sheets. So in terms of shapes and forces, Hooke's law is also an important concept to learn. So Hooke's law basically states that the extension, so the extension essentially is going to be the distance between the original length of the spring and the new length of the spring when you apply a load to it, a weight force. Okay, and it's going to be proportional to the force exerted to restore the spring back to equilibrium. Okay, and that will be equal and opposite to the load force that you will be applying. That's why it's a negative value, Newton's third law. Okay, so the quantity force, at least both load force or restoring force, depending on the nature of the equation or question, will be have a symbol of F, and its units will be newtons. The spring constant will have a symbol of little k, lowercase k. Its units will be newtons per meter. Okay, and the larger the spring constant, I guess the more stiff the spring is, and the smaller it is, the more springy it is. Displacement, which we've discussed already, its symbol is lowercase x, and its units are, of course, being a measure of distance in meters. Now, it's important to note that the equation that you'll use for Hooke's law will depend on what it's asking. So the restoring force is negative kx, but you might be asked for the loading force, which is going to be mass times gravity, and that will be positive kx, okay, because again, Newton's third law, it's working equally and opposite in terms of its action as a force. So be careful with that one. Okay, so a graph of Hooke's law, essentially for the load force versus extension, should be a straight line, and it should go through the origin, because if you have no load, then you will not have any extension on your spring. That kind of makes sense. There is a point, though, where Hooke's law no longer applies. Basically, as you add the loads, you'll see it will increase in a linear fashion, the extension, to a point where it doesn't anymore. It's no longer a straight line. That's known as the limit of proportionality, and you've basically broken the spring. It's now permanently stretched. It's no longer elastic. And that means you can no longer apply Hooke's law. That's known as the limit of proportionality. And finally, looking at multiple springs. Okay, so there's 2 kind of cases. There's when springs are in parallel and springs are in series. So in parallel, which is the case on the left-hand side, you can see that as you apply the weight force to these 4 springs, the extension will be a quarter of what it should be for just one spring. So therefore, the general equation for this is that the new spring constant is going to be equal to n times the original spring constant. Okay, so it's going to be 4 times the original spring constants of those 4 springs. And the second example is when it's in series, and what's going to happen is it's going to actually extend double. Okay, so it means that for that particular case, it's going to be that the new spring constant will be 1 over n, the original spring constants of the 2 springs that you have started with. Okay, so that's pretty much all you need to know for the moment around Hooke's law. We might introduce it again when we look at the energy in springs, But until now, until then, keep up the good mucky.